Hello, everybody. Hey, this is going to be our first lecture for Chapter 10, which is after linear momentum. And what we're going to do in this chapter and Chapter 11 is we're going to review everything that we've done for the entire first quarter plus momentum, and we're going to review it in rotational motion. So you guys, there are three types of motions. There's going to be translational motion, which is essentially a straight line, okay, or a smooth line. Even if it's in a curve, we could get that sort of distance. And then we're going to have rotational distance, and we're also going to have, rotational motion. We also have vibrational motion. So what we're going to talk about here is rotational motion. So obviously, we're going to be moving in a circle. And so what we want to talk about just is some preliminary stuff. And if we have a circle or something that is rotating like a bicycle tire or a car tire or something along those lines, we can think of this car tire is if it's going to rotate, is going to rotate through a certain angle. And this would be theta initial, and this would be theta final. Now, usually when we talk about something, when we start and finish, we usually don't start out with 3 or 4. We usually start out with this being, let's say, 0, and therefore theta would be equal to theta final. Okay. Now, you guys are used to this. In a math sort of sense, where if we know the radius and we know the angle, then we can get the arc length, which we often will call S. Okay, so theta R is going to equal to the arc length, and this only works from a radian. This only works from a radian point of view, so we can't do that with degrees. So we are very much used to talking about degrees, like 360 degrees in a rotation, but not so much in radians. So you guys probably know that if you want to change, let's say, degrees into radians, okay, we would take, for example, let's say we had 60 degrees and we wanted to change that into radians. We are going to multiply by pi and divide by 180, okay? And this would be equal to, let me see, pi over 3, okay, radians. And we do not, you guys, in physics, we do not want to know in terms of pi, but we want a decimal for that, and this would be 1.05 radians. Okay, would be 60 degrees, because if we wanted to go, let's say, 1 radian, and we wanted to get that in degrees, we're going to do the opposite. So we're going to divide by pi, and we're going to multiply by 180. And we can see that this is going to give us 57.3 degrees. In 1 radian. So we can see that 60 degrees is just a little bit more than that. And this is kind of a handy thing to know in your head, to kind of convert from radians into degrees. And if we think about if we went an entire circle, 360 degrees would be about 6.28 radians. So if we take 6.28 times 57.3, then we're going to get to 360. Okay, so that is converting from radians into degrees and degrees into radians. But we also have this sort of arc length here. And so the formula is going to be the angle times the radius is going to give us the arc length. Okay, so if we knew that, for example, that the radius, let's see, if we had a radius of, let's say, 30 centimeters, and we wanted to know how far the arc length is of 60 degrees, okay, then we would take theta r, and that would equal to our arc length. So we would not put in 60 degrees here. We'd put 1.05 radians, and then we would multiply that by 0.30 meters. And we're going to, this would give us an arc length of, let's say, 0.305. Sorry, brain fart. 1.05 times 0.315 meters, and that would be equal to our arc length. Okay? All right, so now we know that there is going to be a relationship between various objects in physics. We know, for example, if we want to know position, position in our common linear sort of descriptions, we would say things like x or y, maybe even z or r, and even s, like we just talked about being arc length. Any one of those would be typical unknowns or the variables for a linear relationship. So if we're talking about rotational, okay, another way to say rotational would be angular. And so typically what we would say, if we wanted an unknown angle, we would say theta, right? In the same way that if we wanted some unknown position might be x, right? Well, another common variable for an angle would be the Greek letter phi, and we could get alpha or beta or gamma. All of these would be typical. All those would be typical sorts of variables that we would use for the rotational sort of sense. So again, if we wanted to know the relationship between linear position and rotational position, I'm just going to rewrite this. It would be theta times r would be equal to s. Okay, so that's conversion from rotational to linear. And now we also, if we talk about velocity, we are going to use v for our linear velocity. And just remember that this is going to be delta x divided by delta t, particularly if we have average velocity. So for a rotational sense, we're going to have omega. Okay, this is lowercase omega. And it's not w. It's not w. We can kind of see these little things going in there. even though it's not W, if you're calling it W, that's fine, because just it's whatever works in your head. Okay, and this would be something like change in theta divided by change in time. And then if it was that, then we would put the average there. All right. For acceleration, obviously, we're going to use A for linear acceleration, and we're going to use alpha. We're going to use alpha for rotational or angular acceleration. All right. And in the same way that if we're going to convert from one to another, we can say omega r is equal to v, and we can say alpha r is equal to a. So we can have both rotational and linear sort of stuff, and their relationship is going to be a function of r, All right, so a lot of times we're going to have something that is going to move both rotationally and linearly. For example, if we had something like this bicycle tire rim, and it was going to move rotationally, right? Sorry, translationally, it would then rotate as it went. So there would be a relationship between the linear and the rotational, which would give us these three relationships. Okay, now it could also move just in place, in which we have a motion that is moving purely in a rotational sense, and in that case, we are going to go back, you guys, we're going to go back and talk about the same kinematic equations, that we had linear as we have rotationally, okay? So I'm going to slide these over, and what I did a few minutes ago is we talk about our four regular kinematic equations from a linear, which would have been average velocity is equal to distance divided by time, which for a constant acceleration, that would be v final plus v initial divided by 2. So we can just see that I have substituted in there the linear variables with the rotational variables, and then we get our other relationships there. Omega final is equal to omega initial plus alpha t. Change in theta is equal to omega it plus 1/2 alpha t squared. So the same sorts of issues. You are going to end up with using these equations to calculate those rotational sorts of questions. And for the most part, that's going to be fairly easy. So, for example, if we have a tire moving with a change in theta of, let's say, 1,000 degrees. Okay, so it's going to go 1,000 degrees, and we're just going to do this in a time of, let's say, 20 seconds with an initial angular velocity of 0. Then what is its angular acceleration going to be? Okay, so if we have this, we might say delta theta is equal to omega it plus 1/2 alpha t squared. So you guys, this is one thing right there where you can get messed up. 1,000 degrees is not what we want. We want that in radians. So if we want to change 1,000, we are going to divide by 180 and multiply by pi. And so we're going to say 1,000 divided by 180 multiplied by pi is going to give us 17.45 radians. Okay, so this right here is 17.45 radians, and that's going to be about 2 3/4 revolutions, about 2 3/4 revolutions. So a lot of times we'll be talking about radians, and sometimes we'll talk about revolutions. And you know that for 1 revolution, there's 2 pi radians, or 360 degrees. All right, to finish up with this, if we know that this is 17.45, and we know that the initial omega is equal to 0, and we know that the time is 20 seconds, so we're going to have 17.45 times 2 divided by 400, and I am getting 8.7 times 10 to the minus 4. So alpha is equal to 8.7 times 10 to the negative 4 radians per second squared. Radians per second squared. And for our purposes, I just want to double check that. 17.45 times 2 divided by 20 squared. This is times 10 to the negative 2. Times 10 to the negative 2. Okay, so that would be an example of how you would calculate the angular. This would be how you calculate the angular acceleration. Okay, and if this was on a car tire, we could calculate what the linear acceleration is, and we would calculate that linear acceleration if we multiply that by whatever the radius might be. And that would give us the linear acceleration at the same time. Okay, so a few other things that we're going to cover in greater detail as we move forward is we think about some of the things that we have covered. Some of the things that we have covered thus far in the linear sense would be something like force. And we know that force in a linear sort of thing would just be equal to ma, and a force would be a push or a pull. Now, in a rotational sense, that would be torque, okay? And we could think of this as a twisting motion. Now, it's kind of easier to think in force of having a direction either in one dimension to be positive or negative. When we talk about rotational, it would be clockwise or counterclockwise would be descriptions to talk about having a positive or negative direction. So a lot of times it won't matter, because if we're rotating, we can just think of it as being in that positive direction. But there's going to be times where we got to talk about clockwise and counterclockwise. Now, so if F is equal to ma, then torque is going to be equal to what's called moment of inertia, okay, times alpha. Moment of inertia times alpha. So this moment of inertia is an interesting concept, and it has to do with the distribution of mass and how it's going to rotate. And we can calculate that by taking the sum of all the mass times their radius squared, So if we had an object here, and an object here, and an object here, and we wanted to calculate what that moment of inertia would be rotating around this point right here, we could take M1, M2, and M3, and we would multiply that by R1 squared, R2 squared, and R3 squared. And we get each one of those M1 R1 squared plus M2 R2 squared plus M3 R3 squared, and we'd add them all together, and we would get our moment of inertia. So that would be kilogram meter squared would be our units, okay? Now, this is if we have some definite finite objects, right? But if we had some sort of object that was regular but not specific individual points, we would add up all these things and we would get this I to be the integral of r squared dm. So again, this is like from an integral point of view, we're taking all of those masses and multiplying it by r squared, and we're adding them all together. And that is where the integral comes from. So we'll continue, you guys will continue to explore that. And we'll talk more about that on Wednesday, Thursday, Friday. So we can also talk about, for example, kinetic energy. Now, kinetic energy in terms of linear would be 1/2 mv squared. When we're talking about rotational, this would be 1/2 I omega squared, because the equivalent of our mass is moment of inertia, and the equivalent of velocity would be angular velocity, or omega. So we can get that sort of stuff too. If we're talking about momentum, which we'll get into, and that's really chapter 11, we would call that P, which is equal to mass times velocity. Well, in terms of a rotational sort of sense, we're going to have angular momentum, which we're going to use the symbol of capital L, and that would be equal to I omega. All right, so we're going to explore a lot more of this in the days to come. But I think for now, the big takeaway and what I'm going to be asking you to calculate here is going to be using these kinematic equations to calculate and get used to those angular quantities. And remember that those angular quantities can then be turned into linear terms, and the relationship between the linear and the angular is essentially going to be radius. And again, we'll talk more about that. And for now, this is it, and we'll see you guys the next time.